Hello there, this is an A-Level Further Maths video. We're looking at the Core Pure Mathematics textbook 1. We're working our way through chapter 1, which is to do with complex numbers, and in this video, section 1.4, we're going to look a lot more closely at quadratic equations when they have complex roots, but also we're going to be looking at quadratic equations in general and some of the properties which we may not have made use of before. So have a look at the question there on the screen. Now I've written a quadratic equation and I've written it in a factorised form because I think that might be easier for us to deal with here. I've put a couple of questions up there for you to think about. Pause the video, have a think about it and restart when you think you've got some answers. Okay, so how did you get on with this? Now, I'm hoping, because I wrote it in that factorised form, that you could just say what the roots of the equation are straight away. The roots are these numbers alpha and beta here. If you substitute x equals alpha or x equals beta into the equation, you end up with a solution. So those are our two roots. Now, the second part of the question, explain why the equation could instead be written in that form. Well, hopefully you saw that all you need to do is just expand the brackets. And if we expand the brackets, we end up with what we need here. So let's just quickly do that. X times x is x squared. X times the negative beta is going to be minus beta x. And then the minus alpha here times x is going to be minus alpha x. So that means that I can combine the alpha and the beta together in the coefficient of x here and write that. And then finally, the negative alpha times the negative beta is going to give me a positive or a plus alpha beta. Now this highlights a fact which we may not have been aware of, even though we've actually been using it for quite a while when we've been factorising quadratics, is that the numbers which go in this position here and here, the alpha and the beta, those are related to the roots of the equation. So when you add the two roots together, you end up with the coefficient or the negative coefficient of the x in the equation. And when you multiply the two roots together, you end up with the constant term in that equation. Now, of course, that only works when we have a coefficient of 1 for x squared, but it's still a useful fact, and actually it's something which you may have recognised yourself when you've been dealing with quadratics, or you may not have done, but it's going to be something which we're going to be using a lot in this video, so worth knowing about it now. So here's the result then. If you want to add together the roots of a quadratic equation, you're going to end up with the negative of the x coefficient, and if you multiply them together, you end up with the constant term, providing, of course, that the x squared coefficient equals 1. So let's see if we can make use of this fact to form a quadratic equation, given that we know the roots. There's a question on the screen. Pause the video, have a go, and restart when you think you've got an answer. Okay, let's see how we get on. We're going to use the result about the sum of the roots and the product of the roots here to get our answer. So if we take our roots, which are negative 5 and 7, and we add them together, we get the answer 2, of course. Now 2 is going to be the negative of the x coefficient in our equation, so that's going to be minus b in our notation that we've got up there. So of course that means that b is going to equal negative 2. Okay, now let's see if we can find the c. Well, the c is going to be the product of the roots, so we're going to take the two numbers, the two roots, multiply them together. In this particular case we get minus 35, so c is minus 35. And if we wanted to write down the equation, it would be x squared minus 2x minus 35 equals 0. There's a quadratic equation with roots negative 5 and 7. So please do remember that fact about the sum of the roots and the product of the roots of a quadratic equation, because it's going to come in useful later. But for now, let's change gear just a little bit, and we're going to look at this question on the screen just to get us back into the idea of using complex numbers. So please solve the equation, use the quadratic formula. You should get complex numbers as your answer. So pause the video and restart once you've got your answers. Here we go then with the answer to this one. So using the quadratic formula, we should end up here with z equals -2 plus or minus the square root of, and when you work out that discriminant, you should end up with -4, and that's all over 2. And then if you simplify that down, you should have ended up with the answer -1 plus or minus I. Now I want you to notice something here, that the roots here, if I write them out separately, we have -1 plus I and -1 minus I. Now do you remember the word we met in the last video, the last section of the book, which describes complex numbers which differ in just the sign of the imaginary part of the complex number? Do you remember what that word was? So in fact what we have here is we have conjugate complex numbers here. So the roots of our quadratic equation happen to be conjugate complex numbers. And this actually is always going to happen providing that the coefficients of our quadratic equation are real numbers. So if we have a quadratic equation az squared plus bz plus c equals 0, if that happens to have complex roots, then those roots will be conjugate complex numbers. And I think that you should be able to work out for yourself why that has to be true. So have a go at that. I've put the question on the screen there. I'd like you to use that quadratic formula to justify that statement, so that if we have a complex roots to our quadratic equation, then those roots must appear as a conjugate pair. Right, so what do you think then? Let me see if I can convince you why this must be true. So if we have our quadratic equation there, and I try and use the quadratic formula, of course I'll just write that down. We should be very familiar with this by now. Okay, so the first thing I'm going to do here is I'm going to just split this up. Actually, I'm going to write it like this because it's going to make it a little bit easier to see what's going on here. So we've got the minus b over 2a plus or minus the square root of the b squared minus 4ac all over 2a. Okay, so hopefully you can see that's an equivalent statement there. Now, let's see what I can do with this discriminant. Now, if we have complex roots, then this discriminant, the b squared minus 4ac, is a negative number, right? So I'm just going to write this down as minus b over 2a plus or minus something negative here. My pen's run out. Let me try another pen here. Okay. So something negative in that square root sign, and that's all still being divided by 2a here. Now, of course, the square root of something negative, that's an imaginary number. So what it means is that this part here, the minus b over 2a, is real, whereas this part here, the square root of something negative over 2a, is the imaginary part. And so you can see that we've got the real part of both our roots must be the same, and the imaginary parts must differ by one's positive and one's negative. So we must have our conjugate roots here. Now, of course, that only works if the a, the b, and the c are all real numbers themselves. If either of those, if any of those was a complex number, then this may not work because we may not have real parts and imaginary parts split up quite like this. However, if a, b, and c are real, our complex roots must appear as a conjugate pair. I hope that made sense. Right, okay, so the fact is that these roots must appear as a conjugate pair if they're complex. So let's just use that idea. See if you can just have a look at the question on the screen and immediately say what the other root of this particular quadratic equation must be. Okay, so did you get this one here? If one of the roots is z, which is 1 plus 3i, then the other root must be the conjugate. Remember the notation here, z star, and that's going to be 1 minus 3i. Right, now it's time to piece everything together. That idea of the sums and products of the roots that we looked at earlier in this video, together with the idea that these roots must appear as a conjugate pair. Let's have a look at this question here. We'll look at this one together as an example. What I'd like to do is I'd like to see if we can work out what the equation is, or the values of the p and q here, given that we know one root of this, this equation here. So let's start off with looking at seeing if we can write down first of all the other root of the equation. So if the first root is 2 minus 3i, the second root must be the conjugate, which is 2 plus 3i. Okay, so that's the first thing to do. Now let's see if we can use the idea of the sum and the product of these roots to get the p and the q. So let's do the sum first. So the sum of the roots, well, that's going to be 2 minus 3i plus 2 plus 3i. Okay, and that just becomes 4. You can see these imaginary parts just cancel each other out here. So that must mean that the z coefficient here, p, in fact minus p I should say, equals 4, which gives us p equals negative 4, like that. Okay, so there's using the sums of the roots, which must become that z coefficient there. Now let's look at the product. What happens when we multiply these two things together? Well, let's just quickly do that. 2 minus 3i multiplied by 2 plus 3i. Let's multiply that out. So 2 times 2 is 4. 2 times the 3i is 6i, but then that's going to cancel with the minus 3i times the 2 here, which is minus 6i, so I won't bother writing that. And instead we end up with the last term, which is minus 3i times 3i here, minus 9i squared, which I can write as plus 9, because of course I squared is minus 1. That all becomes 13, so our product there becomes 13. And so that must mean that the q in our equation is just 13. Okay, have you got the idea? Here is one for you to have a look at yourself. So exactly the same type of question here. I've given you one root of the quadratic equation. I'd like you to find the equation itself by working out the values of p and q. Okay, so here's what you should have done here. The first thing to notice is we can say immediately what the other root of the equation is, because we know it must be the conjugate of the root that was given here. So the other root must be minus 5 minus I. Okay, then we can look at our sum and our product. Add the two roots together. I'll just write down the answer here. You should have ended up with negative 10, which means that the minus p is negative 10, which means that p is 10. Moving on to the product. When you multiply those two roots together, you should have ended up with 26, which tells us straight away that the q in our equation must be 26. So if you wanted to write down the actual equation itself, you would end up with z squared plus 10z plus 26 equals 0. That must be the quadratic equation with the root minus 5 plus I. So how do you feel about this particular topic here? You probably want to get some practice with this. Have a look at exercise 1E in the textbook. Make sure that you can answer those questions, and we'll be back in the next video for the last section of this chapter. Okay, bye for now.